So the ZS which we were taking an example was what? I think we derived something last class, no? Okay, let us do it if we didn't do it. Let's say ZS is equal to 1 by Hj omega square is equal to 1 by 1 plus omega 4, just for an example. And then this should be equal to real part of Z in j omega. So this is equal to 1 by 1 minus s square. Maybe I should take it a bit more complicated one, no? No, S4 rather. I'm sorry, okay. So this, if you expand it, is equal to 4 poles. One pole will be at S plus. I think I did it in the last class, no? And so on, this complex conjugate of this. So now you find the residue of this and residue of this. And if you, how do you find the residue? You multiply this by this function and substitute s is equal to minus of this, and that gives the residue of this. Similarly, find the residue of this, and you got the two functions, double it up because half here, so you get z of s. And the z of s comes out to be s square plus root 2s plus 1, I think root 2s plus 1. If we do all that, what I told you, it comes out to be some this. Okay. So now Miyata method has to be applied on this. What Miyata said was very interesting. Since the transfer function here is 0 only at omega is equal to infinity, there is no other 0 except omega is equal to infinity, and this transfer function, this impedance Z of s is a second order impedance because denominator polynomial is 2. So there should be one inductor, total inductors and capacitors are equal to 2. Now we have one inductor and one capacitor equal number. So this inductor and capacitor must be so used in the network, they create zeros in transmission. You understand this point? Because this clearly tells you this network must have two reactive elements and they must be equal. So there is one inductor and one capacitor, at most differ by 1. In this case is even, so one must be one capacitor and one inductor. They must be placed in the network in such a manner that at omega is equal to infinity, they give you zero transmission, because that is what the requirement here is. So what arrangement of inductor and capacitors will give you zero transmission in a network? If the inductor is series, and then at omega is equal to infinity is open circuit, so nothing goes from this side to that side. If the capacitor is in shunt, at omega is equal to infinity, it becomes short circuit, so nothing goes from here to here. So they must be so organized that the one inductor must be in series and one inductor must be in shunt. So you must somehow use this function and organize this function in such a manner that you get series inductor and a shunt capacitor. Okay. So this is an impedance. So you take it as 1 by s square, because the denominator is higher power, root 2s plus 1 divided by root 2s plus 1. Okay. And now this function is in admittance, right? So when you now you do long division, something gone wrong here. Two of them should cancel. Function is wrong. I don't know, I have it with me or not. You can do that, but no time. I don't think I have it here. Should you do that all that? Find the residues and all that? I think it's 1 by root. Yeah. Now it works. So this becomes equal to S square. That's also wrong. These two terms should cancel.
With that they will cancel.
Will cancel? 1 by root 2. How will I cancel?
1 into root 2
You multiply. You are right, correct. Okay, now you are left with 1. Then again divide in what? One, then you get 1. Divided by 1, so you get 1. Last one will be 1. Now this is what? This is an admittance, because we divided this by this, and this is an impedance, and this is again admittance. So first one is root 2s admittance, which means a capacitor. Admittance of a capacitor is S times something, right? So the first one will be a capacitor of value equal to root 2. The second one will be, because now we inverted it and made an impedance, this is something into S. So this inductor value is 1 by root 2. And the last one is an admittance of 1, which means 1 ohm. Now, this is the network I require, lossless terminated 1 ohm. So the lossless network is equal to this. So this is a filter which will give you a transfer function equal to 1 by 1 plus omega 4, correspond to a low pass filter with a Butterworth characteristics, because there is a Butterworth characteristic of second order, because omega 4, and that will be containing one capacitor and one inductor as it should. And capacitor is shunt and inductor is series as it should, because transmission zeros are all at infinity. So if you put omega 6 here, you will end up into S cube here. So there will be three reactive elements, and maybe 2 inductors and 1 capacitor, or 2 capacitors, 1 inductor. Do the same trick, and then you get a ladder network and terminated by 1 ohm. So the filter design tables that are given in MATLAB are based on this synthesis technique, and the values are now given in a tabulated form. That is the Butterworth of this kind of a network, of singly terminated network, in 1 ohm, then the values are this 1 by root 2 and root 2. If it is next order omega 6, there will be some other values, and so they give table and you read up from the table, and MATLAB simply reads up from the table, and you will never know how the table has come, right? So this is the method by which the table has come, which was credit goes to Miyata. And the beauty of this network is it has a common ground and a ladder network, very nice to synthesize, implement in practice. So everybody uses this kind of filters now of any order. If it happens to be Butterworth, only this will change, and if changes, these poles will change, but method is exactly the same. So you will end up into Chebyshev filters, again the same ladder network by Miyata method. Tables are available for that. And if you want same thing, you can do with Bessel filters also, exactly same method.